And thank you for joining us for our 2025 lecture series at White Mountain Research Center, where we're celebrating 75 years of scientific achievement. My name is Gayleen Kinsey, and I'm the scheduling coordinator here at WMRC, and I will be the moderator this evening. A couple of housekeeping items include to please keep your cell phones silenced or turned off. And the Q&A will be at the end of Bill's talk this evening. This talk is being recorded, and it will be posted to our YouTube channel. And if you have questions about the field trip, if you're registered for it, please approach staff after the talk. There's currently a wait list, and the registration's full, but you're welcome to talk to me afterwards. And with that being said, I'd like to begin with giving a land acknowledgement. The White Mountain Research Center acknowledges the Numu, Paiute, and Niue Shoshone as the first peoples and traditional land stewards of Paihunadu and Ko'otoya, the Owens Valley and White Mountains. As a facility managed by a land grant institution, we pay our respects to our community members, colleagues, elders, relatives, and relations of past, present, and emerging generations. I would like to introduce this evening's speaker. Bill Krebs is a native Californian, born and raised in Los Angeles. He received his bachelor's degree in geology at UCLA and his doctorate in geology from UC Davis. His specialties are stratigraphy, I always murder that word, the study of layered sedimentary rocks, and micropaleontology. Bill's title of his presentation this evening is the Cambrian Explosion in the White Mountains, California. Here he will be discussing the seminal life event known as the Cambrian Explosion that occurred 541 million years ago, which marked the abundance of aquatic invertebrates on Earth and the extinction of many Precambrian life forms. Bill will also discuss fossil evidence of these events in the White Mountains and the ecological relationships that now exist between them. With that being said, Bill Krebs.
Thank you, Gayleen. Thank you, Gayleen, and I would also like to thank the White Mountain Research Center for giving me the opportunity to speak tonight.
We don't have a mic that's going to project him. I can turn off the fan so you can hear him better, but that's going to reduce the airflow.
Well, I can try speaking up.
Project.
Okay.
Pretend you're playing the clarinet.
Oh, get out the cigarettes. I thank the White Mountain Research Center for inviting me to give this presentation, and I thank you, the audience, for coming. I hope you found the presentation interesting and informative. I live currently with my wife, Candy, in a small town in Texas called Round Top, population 87. Both of us here now, so it's shrunk to 85. And I've been coming off and on back to Bishop since 1960, but it wasn't until 2009 that we purchased a place here in Bishop. And so I'm pleased to say that when we arrive in Bishop, it seems like the big city. That's fine by us. Now then, you folks are very fortunate in that you live close to mountains that preserve evidence of a seminal event in the history of life on Earth, and that is the Cambrian Explosion, when fossils, it would appear, suddenly arrived in the rock record in great abundance and in numbers. Prior to that, nothing, or so it seemed. And then to the present day, in younger sedimentary rocks, fossils are not uncommon. And so, in this presentation, I'm going to show you the evidence for this event. I'm going to try to mark it in the rock record here in the White Mountains. And it really is quite fortunate, as I say, that you live so close to these mountains that have this story to tell. All you need to do is to read the book, and you have to know the language. And it's really quite interesting, I think. Okay, next, please.
You ready? Okay.
All right, well, so I'm discussing the Cambrian explosion. And the first question is, well, what is the Cambrian? And then the second question is, what is this explosion? So to discuss the Cambrian, we have to look at the geological time scale, this chart. The oldest part is down here at the origin of the Earth at 4.6 billion years ago. And then we go forward in geological time all the way up here to Thursday, right there. Now then, geological time is divided into two great eons, the Phanerozoic, meaning evident life, and the other one used to be called Cryptozoic because it was hidden life. Well, now we have found more fossils in the Cryptozoic, and it's no longer called the Cryptozoic. It's called other names. And the Phanerozoic comprises only about an eighth of Earth history. The Cryptozoic comprises about 7/8 of Earth history. So this chart is no way linear in scale, not at all. And you see the Phanerozoic is divided into all these periods and then the subdivisions. And the reason is that it's full of creatures, animals and plants, and we can use those to subdivide geological time. They're not present in the Cryptozoic, and so we have a more difficult time subdividing this immense amount of geological time. So let's have the next slide, please. No, sorry, go back. And so you can see the Cambrian period is located right here. And the rocks in the White Mountains span this much time, from the early Middle Cambrian all the way into this period, the Ediacaran. Something interesting about this, I should add. These two periods, the Ediacaran and the Cryogenian, are new periods to the geological time scale, and this has been 200 years in the formation. These two new periods were added in 2004, first time in 115 years that periods were added to the geological time scale. It's called the Cryogenian here, cryo meaning ice, so this is a period of the so-called snowball Earth, when much of the Earth, even down to low latitudes, was covered by ice. And it finally came to an end in the Ediacaran, and it's named after the Ediacara Hills in Australia. So there it was largely ice-free, except there was one major glaciation in here. And now the rocks in the White Mountains span this period of time from the Ediacaran into the Cambrian here. There are no rocks of Cryogenian age here, but they are in Death Valley. So the oldest rocks in Death Valley, sedimentary rocks, are older than the ones here. And the Cambrian explosion then occurred right at the beginning of the Cambrian, right at the transition from the Ediacaran into the Cambrian. And the Cambrian lasted from approximately 540 million years ago to 485 million years ago. So a long, long time ago. Next. All right, let's go back in time about 540 million years and find out what this area looked like. Now, it's a bit disorienting, but if you look closely, you can see state boundaries. And I know it's very difficult, but California's in here somewhere. What? There's Nevada, California. It's more clear on the laptop. Anyway, Arizona, Utah. And of course, you notice something very interesting, that all these states that were formerly vertical are horizontal. And the direction that we call west was north. And, next. And the equator now is just above us. So what's happened in the last 500 million years is that what we call North America has migrated to the north of the equator, and has pivoted about 90 degrees counterclockwise to its present position. Now, these are warm tropical waters. The land here, it was barren. No trees, no forests, no bushes, no grass, nothing, because vascular plants had not yet evolved. So it was a rather grim landscape. And being exposed to the atmosphere for a long period of time, it may have taken on a reddish color from the oxidation of the iron compounds. Also, when there were storms here on the land, there's no vegetation to retard erosion. So of course some was absorbed by the earth and the remaining was runoff. So I suspect down here, about 540 million years ago, there were some real humdinger flash floods at that time. Now these are warm tropical waters, but if you had gone scuba diving there or snorkeling, you wouldn't have seen any fish or stony coral because they had not yet evolved. So we're going way back in time here. All right, next please. And so I have placed approximately the location of the White Mountains in this scheme. These colors you see are paleobathymetry, and the lighter the color, the more shallow, deeper blue, deeper. So you can see that the White Mountains are in pretty shallow water. Next, please. And then I've put here Convict Lake because they're Cambrian age sediments at Cambrian Lake. And they are much, much deeper than the sediments we find here. So it seems as though there was a ramp that went from the shallow water here down into much deeper water at Convict Lake. So this is the setup of 541 million years ago. Very different than today, a strange world. Next, please. So I've discussed the Cambrian, you know where it is approximately. What about the explosion? Well, here are two block diagrams intending to show you the contrast between the Ediacaran, the pre-explosion, and then after the post-explosion period. So the first thing you notice in the Ediacaran is this green swath here. This is an algal mat composed primarily of blue-green algae, or they're called today cyanobacteria. Thick, and on it live some creatures, mostly feeding from the water column, some absorbing nutrients from the water column. They're called osmotrophs. Strange, osmotrophs. And the osmotrophs living today are very rare, but there are some. There's some microorganisms, there are some invertebrates, and the most notable one is the tapeworm. So it lives in a very nutritious environment, and it absorbs nutrition through its skin. So these are called osmotrophs. And in those days, in the Ediacaran, it was the rule and not the exception. These days, that's the exception and not the rule. So these are very strange creatures. These are organisms without organs. These are organisms without organ systems. Very strange world. And you see beneath this algal mat, this ground here. It's a firm ground, it's layered, it's anoxic or disoxic, meaning that it's no oxygen or very low oxygen. And with the accumulation of organic matter, it tended to become sulfitic, which of course is very harmful to animal life. And so this is a mat ground surface, and the mat is a sealing agent. So this does not get disturbed, no evidence of burrowing. We have here some shallow, possibly shallow burrowers, very close to the surface. We have this thing called Cloudina, more on that later. It may have been embedded in the mat. And then we have a few mat grazers and then sessile organisms. So very strange creatures. So then we go through the Cambrian explosion into the earliest Cambrian, and now we have lots of bioturbation. These are creatures that have burrowed into the sediment. The sediment now is rich in oxygen because the particles are expanded and oxygen can get down there. It's now a mixed ground rather than a firm ground or a mat ground. It's a mixed ground. It's an exchange of gases with the water. So you have loose oxygenated sediment with burrowing animals. And there is vertical bioturbation. The algal mat is gone. It's been consumed. And on the surface, we have animals with hard parts, hard skeletons. So we have trilobites, for example, gastropod. We have the top predator of that time. And so very different than we had in the Ediacaran. And this constitutes what's sometimes called the agronomic revolution, a huge change. And it's reflected in the animals and in all other kinds of way. And the modern creatures that live in the ocean today, the invertebrates, can be traced, some of them, all the way back to this event. It's a seminal event, a very important event in the evolution of life on Earth. And it's such an important event that's actually a time marker. It's the beginning of a new eon, the Phanerozoic. Next, please. So the criteria for recognizing rocks of Ediacaran age versus those of Cambrian age There are Ediacaran body fossils, soft body fossils, sometimes, if you're lucky, sometimes, in those rocks. We have evidence of microbial mats in the Ediacaran, planar trace fossils, that is to say, along a bedding plane, but not down in the sediment. And then we have some embedded metazoans, Cloudina, and I'll get into that in a moment. In the Cambrian period, we have the first appearance of abundant mineralized fossils, in other words, fossils with hard parts. And then we get this odd thing, a trace fossil. A trace fossil is just a trace left by an organism. And many times we never find out what the organism is, but we do see the trace. And we can use that to kind of evaluate the feeding strategy and how sophisticated it was. And so this thing is the marker for the beginning of the Cambrian. So when you find it, you know that you've crossed over into the beginning of the Cambrian going up section. And of course, there's plenty of evidence of bioturbation, of vertical burrows. Next, please. Now, as regards to the occurrences of Ediacaran metazoans, they have been found virtually all over the world. And you'll note the Death Valley here and White Mtns. I'm going to focus on two sites because they span the Ediacaran. Next, please. One is Mistaken Point, which is dated about 575 million years ago. And the other one, much younger, about 30 million years younger, is down here in South Australia in the Flinders Range in the Ediacara Hills. So let's look at what are, in fact, the oldest known metazoans at about 575 million years ago. Next, please. Okay, so here's an assemblage of these Ediacaran fossils, these strange creatures, at Mistaken Point in Newfoundland. And here you see a reconstruction of the seafloor at that time. And these things, as I said before, are, for the most part, they're osmotrophs. They're absorbing nutrients from the water. Nutrient concentration apparently was so high that they can make a living doing that. Another interesting thing about these creatures is their body plan is based on fractals. And to do that, of course, it increases the surface area, which then permits more absorption of those essential nutrients to stay alive. This may be a sponge, which of course the sponges are living today. Next, please. So I went to St. John's, Newfoundland about 2 years ago and went into the fantastic geology museum there, and they have these recreations of bedding planes at the shore at Mistaken Point. And here's one of my favorites, Fractofuscus. Once again, the body plan is based on fractals, I think 4 orders of fractals. These things were attached, apparently they were sessile, they did not move, and they're one of the more common fossils in the Mistaken Point fauna. Next, please. And now if we switch all the way down, about 30 million years after that one, into the Ediacara Hills, we get this assemblage. Very different, very strange assemblage. The previous one was fairly deep water. This is shallow. And so you see these frond-like creatures. Here you see what are jellyfish. You see this creature down here, looks like a giant worm, and some of these other enigmatic creatures at that time, all soft-bodied, many of them osmotrophs. Jellyfish, obviously not. And jellyfish continue on to the present day, as do sponges. Next, please. And so here are some fossils from the Ediacara Hills in Australia. This thing is my favorite, I think, Dickinsonia. They're normally not all that big, but some of them can get 1.5 meters in length. So they can get rather enormous. And then you have here a probable jellyfish. Here's Charnia, this frond-like creature, centric creature here. This is a small Dickinsonia, and a variety of frond-like organisms. This almost looks like a trilobite, and so forth. Next, please. And then here are 2 fossils from Namibia. This is Pteridinium, and I'll be darned if one hasn't been found here in the White Mountains in the Ediacara. So it's, and the interesting story behind this is I was reading this manual from 1966, and I didn't find anything in it that I didn't already know. And then I came across this plate, and I saw this. And I was amazed, because this, as far as I know, is the first body fossil, Ediacaran body fossil, in the White Mountains. And here are some well-preserved specimens from Namibia. Next, please. And here are the other Ediacaran fossils that have been found in the Deep Spring Formation and the Wood Canyon Formation in California and Nevada. These two formations are correlative. They're both Ediacaran. So these are some weird creatures, as you see here. This thing was sort of like a sack. It was apparently it was in the sea floor, and then it was filled with sediment. And once again, probably an osmotroph, absorbing nutrients. And then these weirdos here. And this thing I'll spend a little bit of time with, Cloudina. You see this tube here, it's calcareous, so it actually has a hard part, and the tube is annulated. It's sort of a funnel-in-funnel creation. And then this part, the soft part's entirely speculative. No one has any idea, and no one knows what it is. Next, please. Now, let's look at these Cloudina. Some people say they're gathered in such numbers they may have constituted the very first reefs. So here you see a weathered surface of limestone, and here you see the cross-sections of all these Cloudinas. And here it is in the White Mountains. Namibia, the White Mountains. Next, please. And here, from Hines and Loretta Roads, some of you may know where that is, these were etched out of limestone. And so here you see the cone and cone structure. Cloudina. Next, please. And actually, you see some indication there was asexual reproduction. So this is the first indication of sex in the Precambrian. And you see the budding here, and budding here, budding right here. And also there may be the first indication in the fossil record of predation. You see this little hole here? Well, those little holes become larger as the diameter of the test get larger. So it's directly proportional, the hole and the creature. As the creature gets larger, the diameter increases, the hole gets larger. So the first indication in the fossil record of predation. Next, please. Now we're going to switch over to plants, from animals to plants. So this is a modern microbial mat, and this is full of algae. And these things are not found very often because they get grazed. And so they have to occur in kind of isolated, protected habitats. But back in the Ediacaran, they were very common. In fact, you could say the Ediacaran is the age of algal mats, or if you prefer, the age of slime and muck. Next, please. So how do we recognize this in the fossil record? Well, the textures of the rocks can sometimes give it away. There's a texture called elephant skin, another one called wrinkles, and then these things that are called shrinkage, or the fancy name is synuresis cracks. Characteristic is they taper at both ends. It's kind of like a tear, isn't it? So these are thought to have been the consequence of an algal mat. And here you see some more making these kind of chaotic polygons. Polygons. Next, please. And here you see a bunch of these cracks, these shrinkage cracks all over. And at times they coalesce to form these bizarre polygons. Next. This will be one of our stops in that field trip. And then, in the same area, look at these things. Now, they don't taper, and they are perfectly shaped polygons. So those are desiccation cracks or mud cracks. So it's an easy thing to do to distinguish the shrinkage cracks from the mud cracks. And the shrinkage cracks, as I say, have biological significance. Mud cracks do not. Here's a specimen. You see ripple marks, and then superimposed on that are mud cracks or desiccation cracks. So it indicates probably very shallow water, and then a period of subaerial exposure to form these cracks. Next. Next. I'll go back one. So I'm walking up this formation. We're in the sandy part, silty part, and then we finally go, as we go up section, we go into the carbonates, the limestone, the marls. And we finally arrive at the destination of our hike tomorrow, which are these stromatolites. So this is a bed of rock that was once deposited horizontally 541 million years ago, and it's been tilted up. My friend George is sitting up there, and then I trade places with George, and I'm looking down at him in this dry creek bed. So you see the stromatolites here, very tightly packed. They're like toadstools, or pillars, and toadstools, very tightly packed, very competitive for space. And they have been eroded off. It's like a toadstool that's been clipped off. The cap's been clipped, and it produces this concentric pattern you see here and elsewhere. And then in the interstices, it's filled up with mud, which now, of course, is mudstone. Next, please. Now here you see a close-up view, the same thing, all of these very tightly packed stromatolites created by blue-green algae, cyanobacteria. And here you see some of them took on rather odd shapes in this process of competition for space. And once again, the interstices filled with mud and then mudstone. Next, please. Once again, lots of these clipped off toadstools, the stromatolites, mud filling in the spaces. And here you see a nice concentric pattern on this one. Next, please. And also up there, I'm happy to say, you see them in cross-section, a natural weathered cross-section. So you've seen them in planar view, and now you see them in cross-section. And you note how they're convex up, and they're growing towards the sun, because actually, these were formed by algae, by blue-green algae or cyanobacteria, photosynthesizers, and they're seeking the sun. They have plenty of nutrients, but they need the sunlight too. Next, please. Now, I took one of these stromatolites, a loose stromatolite up there, and I sawed it in half, sanded it, put some epoxy on it to bring out the detail. And here you see it. So you see these laminae, and each one represents an old growing surface. And the last one, of course, is at the top. Next, please. And here, let's go to the present day, South Australia, southwestern Australia, the Hamelin Pool, Shark Bay, Australia. And here you see them in abundance in the intertidal. They're all crowded together. So you saw one of 541 million years ago. Now you see one of today. They're all crowded together. The growing surface is the top. That's where the algae is, the cyanobacteria. And in growing, they secrete mucus or slime. And particles get attached or embedded in the slime, and it's the process of deposition if they grow higher. Also, they can affect the chemistry of the water and in some cases possibly cause calcium carbonate crystals to be deposited. So these things are growing up. The reason these things can grow here is that this water out here is quite saline. It's hypersaline. And so the grazers, which normally would eat all this, are excluded. And so this algae can proliferate and then form these stromatolites. Next, please. And here in the shallow subtidal at Hamelin Pool, you see these ripple marks indicating current activity. And here are these individual toadstools or stromatolites. And the growing surface, as I say, is on the top. Next, please.
How old are those?
Oh, I would guess a few years old. I don't know how many. You'd have to count the laminae. I don't know. Oh, and then here's one that's been taken, a living one. It's been sawed in half. You see the growing surface at the top is greenish. That's the algae, cyanobacteria. And then as you go down, you're getting older and older. And here, these are the former growing surfaces, these laminae. These are growth laminae. And notice how it resembles the fossil I showed you previously. Next, please. Now then, we're leaving plants getting back into animals. This is a key marker. This is the key marker for the beginning of the Cambrian period. Sounds strange, but this is a trace fossil. This is not a body fossil, but this is a trace left by a Cambrian organism. And it's Tryptichnus pedum, an odd name. And it forms this rosette pattern you see here of alternating points. Next, please. And here you see a diagram of that. So here you see the rosette pattern here that I just showed you. This would be like on a bedding surface, the one I just showed you. And here it is in 3 dimensions. And here's the bedding plane here, here's the burrowing, and this creature then intersected the bedding plane, and then intersected it here, and intersected it there, and formed this curvature, this rosette pattern. And oddly enough, this has been chosen by international agreement as the marker for the base of the Cambrian period. Next, please. And also in the lower Cambrian, we begin to get trilobites, trilobite trace fossils, and then we find the trilobites later. Here's one, Rusophycus, this trace fossil, and the trilobite burrowed into the sediment, left these depressions, and the depressions got filled with sediment and formed this thing, which is the trace fossil Rusophycus. So it is, these are the molds, and this is the cast. You can see it's bilaterally symmetrical, and you see lots of scratch marks, and that's produced by the legs. So this is behavior, 540 million years ago, and we can evaluate it. Next, please. And here are some in the White Mountains, in the Heartless Formation. They're not real well preserved, but you see one there, and you see another one right there. Next, please. And also at the just at the boundary with the Cambrian, you find a lot of these fossils that are along the bedding plane. They're called planolites. They don't go into the sediment, but they're just right along the bedding surface. And here you see a lot of planolites, and then you see this little thing, and it looks like a very shallow, possibly a very shallow Rusophycus, indicative of a trilobite, but it is very shallow. And we find these trilobite trace fossils before we find the trilobite body fossils. Next, please. And then also in the same point, in the same area, we find this creature. Now this is a, let me get this right, this is the cast of the Cambrian sea floor. So the sea floor was the mold, and this is the sediment that was deposited on top of it. And so you see a creature there at that time went burrowing near the surface, and every now and then it would take a plunge and burrow into the sediment. And so it's now a positive feature on this, but it was a negative feature on the sea floor. So it's indicating burrowing, active burrowing, which is not characteristic of the Ediacaran, it's characteristic of the Cambrian. Next, please. And then, of course, this thing, Scolithus, pretty common, but once again, you notice how an organism entrained the dark particles down below. And so we have clear evidence of vertical burrowing, which is characteristic of Cambrian and younger rock, not the Ediacaran. Next, please. Okay, so why have I shown you all this? It's the prelude to this slide. Here we have the Deep Spring Formation. It's divided lower, middle, and upper. And I'm looking to place the Cambrian Explosion. And the Cambrian Explosion is where the Cambrian Ediacaran boundary is in this section. So let's focus on the criteria that will pinpoint it. Next, please. Next. And here are two places where we find Ediacaran fossils, Ediacaran body fossils. They're rare, but they occur in the middle member, indicating this is Ediacaran. Next, please. Then that Cloudina, that strange calcareous tube, that occurs all the way from the lower member up to about the boundary between the middle and the upper member. Next, please. Then we have the planar trace fossils, and they may go down into the middle member, but certainly they're in abundance up here in the upper member of the Deep Spring Formation. Next, please. Burrows that go into the sediment, sometimes obliquely and sometimes vertical. They become very popular in the upper member of the Deep Spring Formation. Next, please. Then I showed you the shrinkage cracks. They're indicative of microbial mats. Well, they occur about here in the middle member of the Deep Spring Formation. Remember that microbial mats are typical of the Ediacaran. Next, please. And then I showed you the stromatolites, the toadstools. And here's pteridinium, that fossil I showed you. It's from about this point in the middle member. Next, please. And then the first appearance datum, in other words, going up section, the first appearance datum of this key marker, T. pedum, marks the beginning of the Cambrian period. It occurs right about there. So taking all this together, next please, it appears that the Cambrian Ediacaran boundary is about here. It's very close to the boundary between the middle and upper Deep Spring Formation. And this is a lithological boundary as well. So this is where the Cambrian explosion occurred, and these are the various characteristics or criteria used to identify this very important biological and geochronological boundary. Next, please. Now, as we go up section into younger rock, we're in the Polita Formation, so we're now still in the lower Cambrian. A lot of you I know have seen this thing. They're not terribly impressive. They're called archaeocyathids, and they're a kind of extinct sponge. They're abundant in the lower Cambrian, there's some in the middle Cambrian, and then they finally drop out in the late Cambrian. So whenever you find one, you know you're in the Cambrian, probably the lower Cambrian. But as I say, they're less than impressive, they're underwhelming, but there you have it. They're there, and they're there in abundance. Next, please. Okay, well, actually, in life form, in lifestyle, they looked like this. They were these cones you see here, inverted cones. They tapered down. Here was a holdfast they used to attach to the substrate. In this case, these are deceased, dead sponges, archaeocyathids. And then over here's a trilobite to remind you that it's indeed the Cambrian. And here's a very nice specimen I found near Montenegro Spring. And you see the inverted cone, it's tapering down in this direction, and then the holdfast, this stuff is right down there. So it's a really fine specimen. I'm donating this specimen to White Mountain. It's better here than in my backyard. Next, please. And then, of course, we find trilobites, finally. Everyone loves trilobites. I do, too. So here's an olenellid trilobite. It's one of the early trilobites. You know that because of the repetition of segments. There's not much differentiation or specialization, and that's characteristic of arthropods. The early ones tend to lack specialization, and then with time the parts become fused and they get very specialized to the crabs and the lobsters we know today. Now then, a few years ago in 2023 in Morocco, some trilobites were found beautifully preserved in a lower Cambrian volcanic ash. Beautifully preserved. So this was rather like a trilobite subaqueous Pompeii. There was a volcanic eruption and these things were preserved, beautifully preserved. And then these people took, I think it's called tomography, and they looked at the structure of these trilobites. And the next slide, results are just stunning. Look at that. So this thing is about 541 million years ago. I hope I looked that good in 541 million years. But you can see the detail. You can see the legs, the gills, the mouth parts, the mouth area, the antennae. Here's one dangling over. Here's part of one. So it really is extraordinary. And notice how there's a repetition of segments, no specialization to speak of. Another characteristic of these primitive trilobites. I wish that we could find these up here in the White Mountains. Man, that would be something. Next, please. And then also in the Polita Formation, Lower Cambrian, we also find the first echinoderm. So these are the spiny skin creatures in the ocean. You know, these are the echinoids, or sea urchins. These are the starfish. And this is the first one, maybe the first one known. It's got the odd name Helicoplacus. And of course, many classes of echinoderms have pentagonal symmetry. I don't see it here, but maybe I need to have a glass of wine or something. Next, please. And then also a little bit higher up in the Harkless Formation, we have these little blips here. And I'm not sure what they are. They may be mollusks. And there is a mollusk in the Cambrian. They're called the monoplacophorans. And they're very primitive, very simple. They were thought to be extinct until, I think, 1953, when they were found living in the Marianas Trench in very deep water. So it's another one of these stories where they think something's extinct and boom, it appears in these refuges, these really hard to get to places.
Is that forum, as in forum infra?
I'm sorry?
Is it forum, as in forum?
No, these are mollusks. Yeah, they're not single-celled, they're multi-celled mollusks. If that's what it is, and I'm uncertain. Okay, next please. Okay, so to put this all in a grander context, we have here all the sedimentary rocks of the White Mountains, from the oldest down here in the Ediacaran, all the way to the very youngest in the early Middle Cambrian. And all of this then, and then from this point on, here's the boundary between the Ediacaran, come on, Ediacaran and the Cambrian right there, right at this lithological boundary. And so I've marked important occurrences here, and it tells a story. We have the first occurrence, or first appearance datum of Cloudina right down here. A little bit higher up, we find shrinkage cracks indicative of microbial mats, stromatolites in this limestone, and then this body fossil from the Ediacaran, pteridinium, which is one of the more common Ediacaran fossils. And then this all-important occurrence of T. pedum, that is the index fossil for the beginning of the Cambrian. right here. And therefore, as I say, this is the boundary between the Ediacaran and the Cambrian right there. And then, of course, we begin to get the first trilobite trace fossils. Here's the ficus, that burrowing one down into the sediment. And we go a little bit higher, and we finally find the first trilobites at about this point in the Campedo Formation. Higher up still, we find the first archaeocyathids, these extinct, weird sponges. A little bit further up in the section, the first appearance datum of the echinoderm Helicoplacus. And then over here, possibly mollusks. And from here on to here, there's an expansion, a great profusion of the numbers and diversity of not only body fossils, but also trace fossils. So from this point on up, just a huge expansion of the numbers of fossils and the traces that these fossil organisms left. And so the Cambrian explosion occurred down here, and the remainder of the section is, generally speaking, fossil rich. Next, please. Oh, do you recall, could you go back one? Right, you notice how I marked here oncolite. What the heck is oncolite? It's in red. And so it's a little bit different than the story I've been telling you. Next slide, please. So here's oncolite. It's my favorite rock in the White Mountains. You see these little red spheres or spheroids. These were formed by cyanobacteria, our old friend again. Cyanobacteria are busy. And this time, the cyanobacteria glommed onto a little particle and then began to grow out concentrically around a central nucleus, and ultimately formed these oncoids, they're called. And they sat in this limestone matrix you see here. And some of them can get rather large. There's some over there, and then some are quite small. And here's an outcrop of oncolite near Black Mountain. And so there's oncolite right here, and then a shale stringer, just a little thin bed of shale, oncolite, another thin bed of shale, oncolite, and so forth. So this pattern is repeated. This is a rhythmic pattern. And that's, when you see that in geology and rocks, it's telling you something interesting. The problem is to decipher it. What does it mean? Next, please. So I was able to find some surfaces of this shale, and if you look carefully, I admit it's not easy to see, but you see here polygons. And over in here as well, they're difficult to see, but I believe that these are desiccation cracks, indicating that the shale, when it was, it was mud, and it was subjected to subaerial exposure, and it dried up, producing these cracks, mud cracks. Interesting, unexpected. So we have this rhythmic pattern repeated. And the question is, well, what's going on? So I have formulated a hypothesis which may or may not be right in some respects or in every respect. Next, please. So I visualize this forming in a lagoonal setting. There's the oncolite forming here. These waters are hypersaline because of evaporation. The grazers are excluded, and so the cyanobacteria, the algae, just proliferate. It's just a paradise for them. They've got plenty of sunlight, and they've got plenty of nutrients, and no enemies, no grazers. Well, then what happens is base level falls, either lowering of sea level, or perhaps the land rose a little bit. But then this lagoon was isolated, and eventually the waters evaporated. And then you have the deposition of clay on top of that. And clay may have been brought in by the wind, possibly water, but a thin layer of clay. And then later on, base level rises, perhaps a rise in sea level, and this then is re-inundated. And you have the formation again of the oncolite. And that happens time and time again until you have this repetitive pattern. Now, perhaps there are other explanations, and I'm happy to hear them, but it's the one I currently have. Next, please. Okay, so let's switch gears and let's go to the hike tomorrow morning. Meeting here at 9 o'clock, please be on time. We are going to drive over Westgard Pass and then keep driving a bit further, and we will descend down Payson Canyon on 168. We will park here where the Jeep trail in yellow intersects the road here. And then we'll begin our hike up here, and then we finally reach a plateau that undulates. So this is an ascent, and then it's just an undulating plateau. We begin the hike in the Campedo Formation, which is lower Cambrian. This indicates, this strike and dip indicates, that the beds here are dipping to the southwest, like that. And as we hike the trail, we're going into older and older rocks. And finally here, about here, we cross over from the Campedo Formation into the upper member of the Deep Spring Formation, which is also, it's the lowest, earliest Cambrian. And then as we continue on, we cross over into the middle member of the Deep Spring Formation, right about here. Beds are still dipping this way, so we're going older and older in time into older and older rocks. And then we reach this point, and we will look at some of the rocks here and see these shrinkage cracks, mud cracks, ripple marks. And then we'll hike up this dry creek bed in this canyon all the way up to this point. And the stromatolites are right there. The most challenging part of the hike is this part right here. So we'll take our time. Now, as a word of warning, I led one field trip up here some time ago, and there were numerous participants. And to my horror, on the return trip, some of them, rather than turning here, they just continued on down, walking into Deep Spring Valley. And of course, it scared the kidneys out of me. So what I'm going to do this time, I'll put a blue, where it went, a blue surveyor flag right here so that we don't make that mistake again, because that was very unpleasant for them and for me. And then from there, we'll walk back. Now then we'll park at about 6,600 feet. At the stromatolites, we're at about 7,800 feet. So we'll go up about 1,100 feet. And one way, it's about 2.6 miles, so round trip 5.2, about. Next, please. Here's a photo of Payson Canyon. I'm up on the Jeep Trail. I'm looking down at my Highlander. This is where we will park. We'll walk up to the Jeep, the end of the Jeep Trail, down at the bottom, and then we'll walk up the Jeep Trail. Next. And we'll walk on. Here's the Jeep Trail, higher up, and this is the upper member of the Deep Spring Formation, and I'm standing here in the middle member, and it's here that we find all the shrinkage cracks, ripple marks, mud cracks. And from here, just over there, we'll begin our trek up the dry creek bed to the stromatolites. Next, please. And if you were to continue on, this is the middle member of the Deep Spring Formation, and here's the lower member. Next, please. And here are the views you get of Deep Spring Valley as you walk along the Jeep Trail. So looking down in Deep Spring Valley, there's Deep Spring Lake. And next, here is another view of Deep Spring Lake, a closer view. Okay, next, please. Okay, so I'm showing you this picture not to frighten you, but to let you know, remind you that they are up there. And if you feel more comfortable wearing high-top boots and gaiters, then please do so. I've never had any trouble, but nonetheless, I'll be wearing my low-cut Keens. That'll be it. But they are up there, and please be aware of that fact. Next, please. So I began with the Ediacara and a depiction of it, and here's another depiction of the Ediacara in this strange world occupied by strange creatures that absorb nutrients from the water to stay alive. And here you see this giant, what looks like a flatworm, Dickinsonia, Charnia, attached to the sea floor, Pteridinium here, other weird creatures, Swapuntia there. So this is an image of the seafloor back in the late Ediacaran, just before the Cambrian Explosion. Next, please. And here we have the aftermath of the Cambrian Explosion with all these creatures that have hard parts. Here's the apex predator of the time. And then trilobites down here and all kinds of strange creatures, worms. They're burrowing into the mud, churning it up. And the microbial mats are gone. They've been consumed. All right, so with that, I'll say thank you. Thank you for your attention. I have on display here some of the things I spoke of. Oh, I want to add want to add something. Gayleen gave me yesterday this fossil that she said was collected by a student up here some time ago. And I don't know where it was collected. I don't know what formation it's from. But in terms of color and lithology, it looks a little bit like the Deep Spring Formation, possibly the lower part of the Deep Spring Formation, which would make it Ediacaran in age. And these things are definitely fossils. And they bear some resemblance to a fossil called Espedella. And no one knows what Espedella is. In fact, these things may not actually be a living creature, but they may be part of a creature. And some people speculate that they were holdfasts, that there was a frond or a feather-like creature that grew up, and this is how it was attached to the sea floor. Yeah, so this was as of yesterday. And here I've got shrinkage cracks, I've got cross-section stromatolite, I've got planolites here in the earliest Cambrian, Scolithus, Rusophycus, a trilobite here, archaeocyanathids, and then this weirdo rock, oncolite, and then some books of possible interest to you. Yes, please.
I'd like to know if new rock formation occurred primarily underneath this layer, so that most of this kind of stuff has eroded away.
New rock formed underneath?
I mean, yeah, like with a whole lot of other rocks came along later.
Oh yeah, these were all deeply buried at one time, very deeply buried, all these rocks. And then as the White Mtns arose, they were exposed at the surface to where they are now.
Okay, and so some of this has probably eroded away.
Oh yes, there's some, it's gone forevermore. It's just dust. That's true, yeah. We only see the remnants. Yes?
So when you were talking about showing a picture of the stromatolites and the mudstone that's around that?
Yes.
So is that mudstone mud that was deposited 540 million years ago?
Essentially, that's right,
So
yeah.
you're looking at something from that long.
Yes, yeah, it's there. There was the gap, the interstices between these mushrooms, these toadstools, and it had to be filled with something, and it was filled with mud. That's right, yeah. And now it's mudstone.
So as the stromatolites grew, or cyanobacteria, the algae mats grew, their interstices filled in by mud.
Yes, yes,
So
that's
it's not
right.
like the mud was there first and then they grew on top.
No, I think it was filled in. The interstices were created, and then eventually mud flowed in there, and it took up the entire space. I think that's right, yeah. Any other questions? Yes, please.
I don't remember the name of the formation, but the one right around the Cambrian,
Yeah.
it was divided into three periods, lower, middle, and upper.
Deep Spring Formation, yes.
So why were those, because it looked like some of them were limestone, some of them were shale. And they obviously didn't, or maybe I don't think they knew what the animals were and on plants, that that was based on, what were those divisions based on? That's,
Lithology,
okay.
lithology. And subsequently fossils were found in them, in some of them. And that's where I come in as a biostratigrapher. I relate the stratigraphy, which is the layered rocks. I relate the fossils that are found in them to the
You know
layered
how
rocks.
they distinguish the three? Because it looks like it's maybe the same stuff, just in different order.
Well,
Or maybe
I think the lower member is mostly clastic, meaning, you know, sands and shales. I think the middle member is calcareous rocks predominate, like marl and limestone. And then when you get high up, I think in the earliest Cambrian, in the upper member, I think it's dominated by very fine-grained clastics like shale,
okay.
right? But it's based on lithology. Anything else? Yeah. Sorry?
The planolites, those are just at the beginning of the Cambrian, just past Ediacaran time.
The what did you say?
The planolites, the worms,
The worms. Well, the burrowing worms become numerous at the Ediacaran Cambrian boundary, right in that vicinity. And then on up, they're very common. They're very common all the way on up. There are some planar, the ones that don't burrow, but just kind of lived and grew and fed on the surface. Those are what I call a planar. It's a bedding plane, and they just grow there. And then beginning in the Cambrian, it switched, or this new dimension was added. I mean, you can imagine in the Ediacaran, all of these trapped food resources down here that were not taken advantage of by invertebrates. And then finally, in the after the Cambrian Explosion, then creatures began to burrow down in there and began then to use this marvelous trophic or food resource down there.
There's some great exposures on the road to the Eureka Valley, the northern Ninos, where they're so thick, they cross on top of each other.
Oh yes, yeah, there are places.
Amazing.
Yeah, they are. That's true. That is quite true. That is quite true.
Are there some speculations on what might have caused the explosion? And
Oh, there are a variety of theories. One is that a critical level of oxygen was attained in the atmosphere that allowed this increased amount of energy to become available, so that creatures could then start secreting hard parts, which does require energy. And the theory is that finally it crossed a threshold, and they were able to use this additional energy to create skeletonized hard parts.
What would have made the oxygen increase?
Well, initially and in continuing, you've got the blue-green algae, or the cyanobacteria. So they photosynthesize, and as a byproduct of photosynthesis is
Oxygen.
right.
Okay.
So way back in the past, 2 million, 2.5 to 1.8, there's the great oxygenation event, where you had in the ocean a lot of dissolved iron, of all things. And then these cyanobacteria began producing more and more oxygen. And iron was in a reduced state, and it was soluble in water. Well, then this oxygen came along, and the iron was no longer soluble, and it precipitated out. And it's called the BIF, the Banded Iron Formation, that occupied some period of time. And many of the great iron resources that we have in this country and Australia are from that time. It's this dissolved iron that became insoluble and formed the Banded Iron Formation. But I think that's 2.3 to 1.8 billion years ago. Yes?
Do you have any sense of the time scale between the thin shale layers that are separating the alkalites or whatever they are?
The arcolites?
Oncolites.
Oncolites. You mean this stuff here? Oh, you mean the shale? Yeah, the shale strings. No, I'm sorry.
Bands.
Yeah, no, I understand. Now I understand. I have no idea. I have no earthly idea.
Is it possible that it was tidal,
It was tidal?
refilling the basin and then evaporating back out? Peak tides? The moon was closer back then?
Well, I mean, I'd have to think about that. I've arrived at this conclusion tentatively. I don't know.
You asked.
I mean, so, yeah, no, it's cool. No, it's cool.
Any other ideas?
No, you're right, and that's cool. I think this explanation I've got explains all of the observations that I have so far made. A tidal explanation. Well, somehow
over occasionally.
Yeah, I can't rule it out. That explanation is not much different than the one I offer.
I agree.
Yeah, so I can't preclude that. And I will. No, one thing I will say though is that among the characteristics of the oncolite is that it's lensoidal. That is to say, it's not a continual stratum or layer. It occurs in lenses, isolated lenses, and that would suggest that it accumulated in little basins. Whereas a tidal is flat, but there may have been depressions in the tidal area.
But a tide can come up and spill over.
Yes, no, that's true. Yeah, that's true. Yes, that's true too. Yeah. Well, as you say,
And then it would evaporate back out
this
in between.
I can't preclude that. Your hypothesis is, in some sense, very much in agreement with mine. It's a little subtle difference.
It's subtle.
Yeah. I like subtle differences. Next, please. Any other questions?
Well, you'd have to know the rate of deposition. So is there any way to, at least even in a gross way, to get an idea of how much sedimentation there was per unit time, whatever that
In the oncolite?
in the whole thing, in the whole, let's say, upper member, middle member? I mean, can you date it somehow?
I don't know of any volcanic rocks that could be dated there. If there were some, then that might be an option, but I don't know of any. Nothing comes to mind. I don't know of isotopes that would be found in such old rocks, but I'm not an expert on the technique of dating rocks with radioisotopes. So I don't know. I mean, we know the age of the eukaryote has been bracketed, and so you can project those there. but that's about the only way that I can possibly do it. I can't actually go in situ and make a determination. I don't know how I do that, although I'm not saying it's impossible, but I don't know how to do it.
Going back to the ungulates.
Yes.
Accretions of something that started growing, they
Right.
grew around this. Do you know what the center?
No, I don't. That's a good question. There's some nucleus. And when you think about this, the story of the cyanobacteria, I mean, they're not the most exciting creatures, but they're manifested here, not only in these microbial mats, which you saw, and then they're manifested in these toadstools, these stromatolites. And then finally, the last gasp, you see them in oncolites, way in the Cambrian. So there are three manifestations of the same cause. So, yes, please.
Is there a modern equivalent to the oncolites?
Yes, let's see. Yes, they are occurring in the modern world. I think some are occurring in lakes. I'm trying to think about marine environment. I wouldn't be surprised if they occur somewhere in the Persian Gulf, is my guess. And Sabkas. But they have been documented elsewhere. That's something to look up. That's a good point. But I know they are in existence. I think both freshwater and marine.
I think they're in I think I went by a place once, went out on a boat, looked for them, and they were in the Caribbean. So.
Oh, is that right? Okay.
Yeah.
Or were they large like? There's a difference between oncolite and oolite. Mm-hmm. Oolites are these little tiny, and those are considerably bigger. Yes, and I think I don't think oolites are generally biological in origin, whereas these are definitely biological in origin.
The banded iron formation, was that 2.3 to 1.8?
Well, you have to.
Million
I think of the great oxidation event, which I think corresponds to the banded iron formation. I think it's about 2.3 to 1.8. I think.
Okay, I just wanted to know.
But you can get online and look it up for a more definitive, accurate answer.
So, does metamorphosis destroy the evidence of and do any fossils survive the metamorphosis?
It depends upon the degree of metamorphosis. If it's a mild degree of metamorphosis, then no, you can still find fossils. But if it's a high degree of metamorphosis, the rock is completely recrystallized, and anything that's organic there is obliterated. And here, I mean, these rocks have been deeply buried. They've been altered, but you can still find fossils there. Yeah. Next, any other questions, please?
Bill, I'd like to look at some of those slides again. Can you make that presentation available?
You sure can.
Yes.
Without watching the presentation, I just want to look at the slides.
Oh. Well, I'm gonna post them to a site called researchgate.net. I'm not the only one here who does that, but
You have to create an account, or you can kind of casually browse, but there's more features available if you have an account. So.
Well, from far back here, some of the font was a little small. So.
oh, well, I learned a lesson now. Yeah, I know, I understand. So you folks, like I say, you folks are very fortunate. You live next to this giant book called the White Mtns, and all you need to do is to know the language, and you can read the book. And it's really quite interesting here. Next, yes.
Well, what was the monster, the big top predator?
That's called Anomalocaris.
Can you describe him?
Well, it was a good-sized arthropod. I think it got at least a meter in length, maybe larger than that. Yeah, so it was quite large. It was an arthropod, and it was a carnivore. And they find it, I think it was first found in the Burgess Shale of British Columbia by C.D. Walcott in 1909.
Misidentified it. They first misidentified it.
Okay, yes, there you go, yes.
Yeah.
And so it's an interesting story about the Burgess Shale. So Mr. Walcott identified this, found the site, and it's the preservation is just stupendous. They call it in German, Lagerstatt, meaning a treasure trove. So he wrote these monographs of all these exquisitely preserved fossils. And then I think beginning about the 1960s or the 70s, an Englishman by the name of Conway Morris re-examined these specimens. And he found that Walcott had done, of course, a very good job. It was pioneering work, but he had shoehorned in some of these creatures into existing phyla. And in fact, what he found were creatures that didn't belong to any of the known phyla. And so early on in the Cambrian, you have this plethora of new animals and new phyla. And just like the technology, you know, when the computers arrived or cars arrived, you had all these different brands, and then there's a winnowing out process. And so if I can draw an analogy to the Cambrian explosion, you have all these different forms and then a winnowing out process, such that today, you know, we have some of those phyla from the Cambrian are extinct, and many of them survive to this day. So that event, the Cambrian explosion, the modern world can trace, the modern ocean can trace its ancestry all the way back to the Cambrian explosion. It was that important event. And then before that, it's a different world entirely, where creatures are absorbing nutrients from the seawater, most of them. And they've got this fractal body plan.
Includes us too, right?
Sorry?
The chordates, so it includes us. It's supposedly with chordates go back then.
Well, I think there are some, yes, there are some chordates. There's this site in China that has even older, beautifully preserved Cambrian fossils. And there are the predecessors of the chordates in here. So you look at this thing and you think, gee, that's what I looked like 540 million years ago. That's what my body looked like, at least. And then there's a book on the Cambrian Explosion, and I confess it's a hard read. You kind of have to sift through to get the gems, but there is a book on it. And then lastly, you're most welcome to come up and look at these specimens. That's why I brought them. And then I have here a simplified geological map of our field area. Yes, please.
That shiny leopard-looking rock, has that been polished?
This one right here?
No, over there, the one with like a leopard body and everything.
This thing?
Yeah.
Yes, I took a chunk of it, I sawed it, and then I sanded it and put some epoxy on it.
Oh.
It's sort of a cheap man's polish. The only proviso is you can't leave it in the sunlight because it tends to turn yellow. But I don't, so.
Hey, Bill, there's a couple of geologists that are interested in this relationship. They realized that the moon was way closer at one time, and the way they did that was animals put down layers. They put down, like your ammonites and all that, they put down layers on a monthly cycle, a 30-day cycle based on the moonlight, because it would come up. And when they look back at fossilized ammonites, they realized all ammonites were closer together. And that's how they determined that the moon was way closer to the Earth.
Yeah, actually, I anticipated your question. I got online, I looked up the length of day in the early Cambrian. And what I found is that, according to online, that it was 21.8 hours, the length of day. So the Earth was spinning faster. The length of the year, they estimate, was 400 days. And the distance from the moon is now, currently averages, now it's about 239,000 miles now. And they estimate that in the Cambrian, the early Cambrian, it was about 230,000 miles. So a little bit of trivia you can bring up in a contest. Okay, well, I thank you very much. And I hope to see some of you on the field trip tomorrow.